Hello, and welcome back to Humanity First. Hopefully you like the setup. I am trying to experiment a little bit with the setup to make it better if possible. So hopefully this is better. The only issue is I think the camera might be a little bit shaky. So we'll see the quality of this video and then I guess go from there. But today I wanted to talk about a pretty small thing, so hopefully this shouldn't be too long, but I wanted to talk about the most recent findings that were released by METR. So if you remember, METR is like this organization that is really well known for evaluating how good a model is, because you can imagine, like with, and you might have experienced this yourself, if the only thing you're using the models for is just as like a chatbot, you might not experience a very large jump in performance from one model to another. That general like sense that you have for how good a model is just by chatting with it, just by talking with it. The models are already so good as a baseline that it's hard to detect if a model is actually significantly better than a previous generation of models. So people have to rely on other techniques for getting at model abilities. And METR is most well known because they're kind of like a trusted third-party lab, and they test all the models of the frontier companies. And the metric that they primarily use, that they're most well known for, is the abilities of models to complete long horizon tasks, where long horizon task here just means a task that would take humans significant amount of time to accomplish. And primarily they focus on essentially software engineering tasks. It can be like cybersecurity, just general software engineering questions and challenges. And they evaluate how effectively a model is able to perform these tasks compared to the human baseline. And particularly, we talked a little bit about how they calculate the metric that they use for what models are, where essentially what they use to rank the models, the parameter that they use to that they report. And essentially what they do is they have a very broad array of software engineering challenges, and they give it to a bunch of engineers, and then they record how long it takes the engineer to complete the task. And so you imagine you have many different kinds of tasks, and you have many different engineers. So for each task, there will be a distribution of when the engineers in their sample group, how quickly they were able to solve this particular task. And so they take the average of that, and they will fix that as the average time that would take a software engineer to accomplish this task, for example. And then they give the exact same tasks. And I think they mentioned that they add some extra context and scaffolding for the models, but they measure that same task and give it to whatever model they're evaluating and see how good the model performs, whether it's able to solve the problem or not. And so you can imagine that tasks that would take software engineers shorter periods of time, that those tasks would be easier, and so that the model would perform generally better on those tasks. Whereas tasks that would take humans longer and longer periods to accomplish, those would be more difficult for a model to accomplish. So its success rate on those tasks would be lower. And so they get essentially a distribution over time that gives you how the model is performing in all the different tasks in the different time segments, based on how long that task would, how long it would take the average software engineer to solve this task. And the number that they report is the 50% crossover point. So if METR, for example, says that a model is that if you see in that 50% success rate plot, if you see that a model is listed as, like 1.5 hours, what that means is that if you give this model a task, a software engineering task, if indeed their study generalizes, then what it means is if you give their model some software engineering tasks that would take your average software engineer about a hour and a half, then you should expect the model to be able to perform that task about 50% of the time. So there's like a 50% likelihood of success that the model would be able to accomplish this. So they have been releasing pretty steadily their findings about the models. And so that explains the y-axis. The x-axis is when that frontier model was released. So when you look at the plot, that gives you when the model was released. And what they see, if you look at the plot that they have, is a beautiful exponential, like a almost perfect exponential, where essentially models are doubling their time according to this metric, this 50% metric, every roughly 4 to 7 months. And so I think yesterday was a big deal because Anthropic finally released the results on their of their evaluations of Opus 4.6, which is Anthropic's new model, and it's considered by many right now to be essentially the best coding model that is out there. And from my own personal experience, I feel like that's probably pretty true. And it was a huge jump in performance. So I think the last model, the Opus 4.5 model, that model was released in November, and it was at something like 5 hours to 6 hours. Like that was the range of tasks that it could accomplish. That's what was where it was at. And now you have this new model, which is Opus 4.6, and that was released in February, so this month. And I think it was like around like 13 hours or something for this new model. So that's a huge leap. So it means that for this one company, Anthropic, they went in essentially a 4-month period, they actually more than doubled. And that 4-month doubling rate would be considered like on the higher end of the estimates that have that METR is like tracking or following. So this is a very massive leap in performance. Now, there is some discussion because the tasks that METR has do a pretty good job of giving you high resolution in tasks that would require lower amounts of time to accomplish. So they have a lot more tasks that require shorter periods of time than they have tasks that would require like very extended periods of time. And it kind of makes sense because it's much harder to get test subjects when they have to essentially accomplish tasks that would take them over 24 hours. So you would need to pay them a lot more, I guess. But yeah, so they have essentially less tasks that would on the higher end of the scale. So as we go further and further outside, that nice like sub 12 hour or sub 8 hour range, you are getting the error bars kind of increase because there's a lot more tasks. Or sorry, there are a lot fewer tasks. So there's that caveat, but to be honest, really the ultimate METR's results are meant to be only indicative of a wider trend. And the question is, does these results match what your standard software engineer has been experiencing as they've been interacting with these models. And to be honest, I would say the answer to that is probably yes. I did notice a very large increase in the capabilities of Anthropic's models between the release of Opus 4.5 and the release of Opus 4.6. Like when you use a tool like Claude Code, there is a big jump in performance, a noticeable jump in performance between those two models. And I could easily believe that I think it's a reasonable approximation that Claude can accomplish a task that would take your average software engineer who's unassisted about 13 hours to do, and it's about a 50-50 toss-up whether Claude would accomplish this task or not. So you can give it a task that would require a human unassisted software engineer that long to accomplish. And I think my sense is, yeah, you can expect Claude to accomplish that about 50%. I would think it's about 50% likely to be able to accomplish that. Of course, it depends a lot on the task. So on like certain tasks, especially when you're starting brand new on a new project, that's when you can really trust that Claude will do a pretty good job of coming up with something that's very appealing, that kind of makes sense if you give it a well-defined goal that would take a software engineer 13 hours to accomplish, for example. I would be pretty confident in Claude Code being able to do a good job there. For a large established code base, it's, I would say, having really long horizon tasks on an already existing long horizon code base can be more challenging for the model. But that is really because I think the factor that the limiting factor is the context window. So like Claude Code only has a certain amount of context that it can keep. And so if you have a really large repo, and they're always like pushing the frontier on the context, that's of course the next big thing that everyone's really focused on, because I think a lot of people feel like this is like the limitation right now, is the context. The models are already very capable. It's just their memory isn't big enough to keep everything that they need to know if they're working on a very large project or a very long-term project. They don't have enough memory to be able to store enough of the relevant information to actually be able to continue working on this project effectively. So people are working on this area, and Anthropic actually recently released versions of their models that have 1 million token context length, which is a big jump over their previous models. So they're working on this. But all of this to say that I do think that METR's most recent results do line up with my own experience, and I think with the experiences of others as well who have been using and interacting with these models. So what's the significance of this? Well, I mean, this is just like, again, we talked about, it's like, it's like just because you're not paying attention to what's happening with these models as they're developing doesn't mean that the models are not improving. They are improving, and they're improving at a very fixed rate. And if anything, they're improving faster than those trend lines, those 4 months or 7 month doubling rate, than those would indicate to you. There was a lot of discussion after the release of these results that maybe model development is hitting a hyper exponential. It's actually not a strictly exponential function, but maybe it's a hyper exponential, which means that, so if you're a strict exponential, then the doubling rate remains constant. So like a 7 month doubling rate, it would mean for your first increment you double by 7 months, and then next increment you double by 7 months again, and so forth and so on. whereas hyper exponential, I suppose the way that people use it in this context would be that the doubling time is shortening. So that's an even faster than exponential process. And there are a lot of reasons that people suggest that this can be possible. Obviously, the biggest reason might be because you're beginning to get self-improvement. The models are contributing very significantly to their own research, to their own development, and speeding up the timelines. There's a new factor, a new large factor that is pushing up that exponential curve. But to be honest, whether it's exponential or whether it's an exponential with a 7-month doubling rate or an exponential with a 4-month doubling rate or a hyper exponential, it really doesn't really matter. All of those are extremely rapid takeoffs. Though I suppose it would affect things like in terms of planning, both for your own life and also if you think that this technology is dangerous and you want to take steps to try to prevent its development. But I think it's incumbent to always keep in mind that things might go faster than expected. As aggressive as the timelines are, it's not beyond question that you might have, they're actually predicted to be processes that would lead to a faster than exponential growth. And that would shrink timelines even more. So anyways, I think we need, it's kind of hard because all these episodes are so sad and negative and defeatist. But I mean, that's just the state of things right now. Anyways, thank you very much for listening, and don't forget, winter's coming. All right, take care.